So just now I learned what a functor is. I had encountered this term reading about functional programming, Haskell, Scala, a couple other things I think. And the answer of what a functor is, I believe, is it's like a data structure that can contain a data type that you give it that has some functionality embedded into the data type. So that might sound kind of abstract. So as an example, let's say you have a set. You want to be maintaining a set of objects, and one thing about a set that you need to be true for the set to be valid is that there are no duplicate objects in the set. Like each object is distinct. And so one thing that, if you're adding an object to the set, one kind of functionality that you would want to have is, say if I add an object to the set, I want to make sure that before I add it, that there's not, another object just like it does not already exist in the set, so that I can maintain my uniqueness of all objects in the set. So bringing it back to what a functor is, the set that I'm maintaining, the set of objects that I'm maintaining would be the functor, and each individual object, or like the type of the objects that I'm containing in the set, would be the type that I am giving to the functor. And that type, maybe the data type would be like an integer or a color or some sort of thing that you could compare with different instances of that type. And the functionality that would be included in the type given to the functor would be comparison. So as I said with the set, we want to make sure that whenever we add an element to the set, we want to be able to, to enforce the uniqueness, we need to be able to compare the new thing to be added to the set with everything that's already in it. So we need some sort of comparison function defined somewhere. And the way that where we define that is in the type itself, in the data type. So the data type would maybe have an attribute for the value of the data, and then it would maybe have a function for comparing it to another instance of that type. So if I have two instances of the type, as I have numbers like integers like 1 and 2 or -5, I should be able to, if all of those are instances of integers, I need to be able to have a function that can compare instances like, oh, is 2 equal to 2? That's true. Is 2 equal to 1? That's false. So that sort of functionality is built into the data type. And so, yeah, just kind of to recap, the functor would be the collection or the data structure that you're maintaining. So the example that I gave was a set, but if you're a computer scientist, you would know that there are other types of data structures out there, not just sets, but maybe a list of objects, like an ordered list of things, or an array similar to a list. You can have queues. You can have like a binary search tree, a binary tree, which maintains, in the same way that a set maintains uniqueness, a binary search tree maintains order of your objects. So if I had a set of integers, in a set that needs uniqueness. So then my data type that I give to the set, or to the functor in this case, which set is the type of functor, needs to have a comparison method so that I can maintain the uniqueness of the data in my functor, or in this case, my set. But if I'm maintaining, say, a binary search tree where I need all of my data to, where it kind of sorts my data for me on the fly, in that instance, I need to have not just a comparison of whether or not something is the same, but I need to be able to compare whether something is greater than or equal to or less than another object. So in that instance, it's not just a relation of is it the same as, but it's a comparison of is it greater than, equal to, or less than. So an ordering property rather than a sameness property. And another example, let's say I'm storing colors. I can have a set of colors like red, blue, yellow, orange, etc. That is something I could have a set of because I can test, oh, is this shade of color equal to this shade of color defined in some way that I choose. One way that with the integers, you could have a binary search tree because you can have ordering on integers. We all know that you can test whether or not an integer is greater than or less than or equal to another integer. But for colors, colors don't necessarily have that ordering, or in mathematical terms, that transitivity. So like I can't maintain a binary search tree of colors easily. Though I guess it really depends on how you define the color. If you define the color in terms of its wavelength or its frequency in terms of the electromagnetic spectrum, then you could have ordering. So it all comes down to how you define the function of the functions that go with your fundamental data type. So if I have a color, I can define a function for comparison of sameness. Maybe if I wanted to, I could define a function of ordering, a comparison on ordering. If I have integers, it's a little more straightforward. We all have very intuitive definitions for sameness and for ordering. And once I have that data type, where functors come in is a functor is a way of storing that different instances of that data. So I can have a set where every element in the set is of a certain data type that maintains some sort of structure where there are no duplicates in the set. I can have a binary search tree, I can have a list, I can have an array, I can have, there are a couple of other, data structures out there. I don't know if a graph would be part of this, though it might. I don't see why not right now, but I don't see necessarily why necessarily either. But yeah, I just learned this. It had been on my to-do list to look this up for about a week or two, and as in a moment of distraction at work, I was like, you know what, it's snagging me. I'm going to look it up. And so I read a couple of very useful answers on Stack Overflow, and I want to thank them. And if I post this on YouTube or Vimeo or whatnot, I will post a link to those resources. Hope this helps. Happy learning.